Right, this is the solutions to our review quiz 2. Our first problem we had, we needed to find dy dx, and it looks like this would be an implicit differentiation problem. So with the implicit, and really with related rates, what we've been doing in class, that is a form of implicit. So let's work through this problem. So we need to find dy dx when x is equal to 1. So let's see, the first one we're going to have 6x and then plus 2 times, and remember this is the product rule here, so we have first times the derivative of the second, dy dx, and then plus second times the derivative of the first. The derivative of x is just 1. And then we have plus y squared. Derivative of that is going to be 2y dy dx. And all of that would be equal to 0. And now we're going to go back and plug in a 1. So we're going to have 6 plus 2 times dy dx plus y. We don't know what y is, so we're going to have to come over here to the corner of this and see. Well, let's plug in 1 and see what we get for y. So if we do that, we have 3 times 1 squared, so 3, plus 2y, and let's see, plus y squared, and all of that equals 2. And so let's see, it looks like we can do some rearranging here. We have y squared plus 2y, and if we move that 2 over, we're going to have plus 1 equals 0. And if we factor this, we get y plus 1 times y plus 1, and of course equals 0. So it looks like y equals negative 1. So now we have a value for y, so we're going to come back over here and plug in our negative 1. So let's see, plus a negative 1. And then let's see, on the outside here, plus 2y. So that's going to be minus 2 dy dx. And that equals 0. So let's see what we can do here. So I have 6 plus 2 dy dx. And keep in mind we're solving for dy dx. Minus 2, because we have our distributive property here, so don't forget to multiply out here. And then minus dy dx, minus 2 dy dx equals 0. And let's see, if we can combine our like terms here, well, that gives me 4. But notice when I combine these, I have a positive 2 dy dx and a negative 2 dy dx. That's going to give me 0 dy dx's, and that equals 0. So at the end of the day, this problem ends up being 4 equals 0, which is crackhead thinking. We're not crackheads, so I would say that our final answer is E. Okay, for number 2, let's see. If y is a function of x such that y prime is greater than 0, so I'm going to stop there. That tells us a tremendous amount. If y prime is greater than 0, well, what in the world does that mean? Well, if y prime is greater than 0 and notice it says for all x's, well, that just means then that we can say that y is increasing for all x. For all x. That's important for us. If we're told that y prime is greater than 0, so wow, automatically we could probably stop here and say, well, y has to be increasing for every stinking value of x. Well, that looks like we are going to be able to get rid of c because here we are decreasing. And, well, we're not, let's look right here. We are decreasing here, right? So let's get rid of that, because this says that we would definitely need to be increasing everywhere. All right, and now let's look at our second part that it's telling us. It's saying that y double prime is less than 0. Oh, well, that tells us something awesome too. Y double prime being less than 0, then y is concave down, like a frown. So we have concave down. So, and that's for all x. So we have a frowny face looking. So concave down, well, A, that's concave up like a cup. We can't have that. And E is, well, E is just strange. We've got some concave up through here and some concave down through here. So that means we have B for our answer choice. Okay, for this one we had to find a point of inflection. So let's review ourselves on what in the world is a point of inflection, because we probably don't remember, and that's okay. That's what we're here reviewing for. So let's see, a point of reflection, the first thing you do is find what's called PPOI, which is a possible point of inflection. That's where you find the second derivative, set it equal to 0, and solve. And then the reason why we say it's a possible point is because the second part, we have to have a change in signs. So we have to look for that. Okay, so our second derivative, and we all can find that second derivative. Let's go through here and see. So let's see, y prime, that first derivative, that's going to be 20x cubed, and then minus 5x to the fourth. And now let's do our second derivative. Our second derivative is going to be 60x squared minus 20x to the third. And so let's see. Now we need to solve, so let's set this equal to 0 and solve. And remember, we could probably sketch a pretty good graph of this. So I'm going to say 0 equals, and I'm going to move that negative 20x cubed to the front because I don't like that larger exponent being back there, plus 60x squared. Factor this, so I'm going to factor out a negative 20x squared and find those zeros for that trinomial. So let's see, or not trinomial, sorry, for that cubic function. Lord help us. All right, so that's going to leave me with x minus 3. So it looks like I have potential zeros at x equals 0 and at x equals 3. So here, a possible point of inflection. So that means we can get rid of C, right? Because this doesn't have x being a 0 or a 3. And we can get rid of E. So notice we're either going to be at 0, 0 or 3 and 162. So let's look at, I always do a quick sketch here, or we can do a number line analysis, either one. If we do a number line analysis, let's just look through that right quick. We have 0 and positive 3, and the number line analysis just means we pick numbers between 0 and 3, and we plug in, and I would plug into the factored form because we're looking for sign changes here. We're looking to see, well, did my sign change? And if I had a sign change, then I have a point of inflection. So let's pick, let's see, over here past 0, if we pick a test point of, I don't know, let's pick -1. Now I'm just interested in the sign. Well, notice this out here, no matter what, this little booger out here is going to be negative because x squared is positive, no matter what. So that's going to be a negative. And if I plug in -1 inside the parentheses, So I have a negative times a negative. So this side over here, that's always going to be positive. Well, let's pick a number between 0 and 3. Well, if I do that, let's see, I'm going to pick maybe 2, 1. Doesn't matter. I'm going to pick 1 because I'm lazy. And again, that outside, no matter what, is going to be negative. The inside, oh, let's look. That inside's also going to be negative. Ooh, so that means I have a positive. Do I have a sign change here at 0? Well, heck no, I have from positive to positive. It doesn't change signs. So that automatically throws out anything dealing with 0. So it looks like B is my only choice. I would check a point over here, maybe choose 4 just to make sure I do have a sign change and didn't mess up my signs between 0 and 3. And if we choose 4 over here, again, that outer part stays negative, but 4 minus 3 is a positive, and I do have a sign change here at 3. So that means that I'm going to have a point of inflection at B. Now, if we wanted to graph it, because I'm a big fan of just graphing these, I really am. Here I do have a cubic function, and so, the cubic function is negative. Well, a positive cubic function, remember, it looks almost like the tangent, but with it being negative, it's going to flip it over, and so we look something like that. And so we have to be careful with the graph of it. And then let's go ahead and see, that looked like a spider when I got done. So if we graph it and we're negative, but notice we're squared right here at 0, we're going to have a bit of a bounce. So we're going to come down and we'll cross the x-axis there, or we'll touch the x-axis, but we won't actually cross it. And notice that we're positive on each side, so really I have something that comes down and bounces and then goes all the way up and then actually comes back through. So our cubic looks something like that, as strange as it is, and should not be pointed, it should be rounded, but you all know my drawing abilities. Alright, so for number 4, if the function f is continuous for all x, so for every x there's a y, f has a relative maximum. So f having a relative maximum, that means f prime was equal to 0, or f prime could be undefined. So we tend to forget that. Relative maximum is just a classified critical point. So we do have to remember that means the derivative was 0 or undefined, somewhere around in there. And also for f to have a relative maximum, that means f prime went from greater than 0 to less than 0. And let's see, so that happens around -1, 4, and a relative minimum. So it's basically the same statement with your inequalities flipped. So let's sketch a graph here. What does that mean? Well, -1, 4. And so I either have a rounded point there, but now I could, don't fall into, it's a trap here. You could have a pointed there, so be careful. And the same is true over here at this other point, 3, -2. Could be rounded, or it could be pointed. So I always think it's a trap there. We don't know. We are continuous, so I know these 2 points have to connect each other. How they connect each other, who knows? It could do loop-de-loos all over the place, but those 2 points have to be connected. Well, we're so tempted to say all of this stuff here. Now, as far as point of inflection, that's a second derivative. We don't know anything about that. We just know some of this information over here about the first derivative. F prime at -1 has to be 0. Well, no, it could be undefined, so that's a trap. It's a trap. Let's see, horizontal, that would mean horizontal asymptote there. No, don't know, horizontal tangent, not necessarily. Again, we could have these pointed areas, so I think all of that's just a trap. But one thing, beyond a shadow of a doubt, that I know has to happen, that graph, since it's continuous, and we have that relative min and that relative max, we are probably going to have to intersect both of the axes. So I think number 4 should be E. All right, number 5, the mean value theorem guarantees the existence of a special point on the graph of y equals the square root of x between 0 and 4, 2. What are the coordinates of this point? So let's wrap our minds around what this little booger is saying. So we've got our graph here, and again, y'all, well, good grief, what an awesome graph that is, I tell you, folks. All right, let's see if I can't get a little bit better. I'm trying to get that to hit at 0, but it ain't working for me. All right, y'all close your eyes and pretend. So right there is 0, 0. And 4, 2, so over 4 up 2, so here's 4, 2. And 0, 0, goodness, this might fall apart on me. So there's the graph y equals square root of x. Mean value theorem. Mean value theorem, MVT. Let's see, we've talked about mean value theorem. I think pretty sure that mean value theorem is telling us that we have some c inside the interval AB, so that the derivative, that function's derivative value at c equals f of b minus f at a over b minus a. And you see mean value theorem, you have to think about I rock equaling A rock, or the slope of the secant has to equal the slope of the tangent. So, well, let's see, it's guaranteed. So what are the coordinates of that point? So it wants the coordinates of the tangent line at some point between 0 and 4. So since it's the mean value theorem, it might almost be the average, but let's not go crazy there. Let's see. All right, so let's see. Our slope, let's find our slope. Well, we've got 2 points, right? So we would say 2 minus 0 over 4 minus 0. So 2 over 4, or 1/2. Okay. So what? What does that mean? Well, that means I've got this portion figured out. That value is 1/2. Now, if I knew what the heck this was, life would be happy, happy, happy. Well, let's see if we can figure that out. Well, if y equals, we've got y up here as the square root of x. So y is x to the 1/2. So let's find the derivative of y. Y prime equals 1/2 x to the negative 1/2, right? Well, okay. So I want to really find that c value, or that x value, so that this derivative, this is the f prime, my gosh, at all these lines, that's this portion. So we need to set these equal. So I have 1/2 x to the negative 1/2. That represents the slope generator. And thank you, Stacy McMillan, for that term. But this is the slope generator for all of these tangent lines. I just need an x value, and then I know what the slope of that tangent line is. Well, it's saying, hey, I want that slope of that tangent line is really 1/2. So if we solve this, well, x to the negative 1/2, well, those 1/2s cancel out over here, like that cancels with that. So I'm left with 1, not 0. Crackheads put 0 there. That is 1. You're not subtracting, you're dividing. So let's see, x to the negative 1/2 equals 1. Well, the only x value that's really going to work for is 1. So I think we found it, didn't we? X has to be 1. So let's look over at our answer choices. Where do I have an answer choice where x is 1? right there. All right. So again, mean value theorem. Every time y'all see mean value theorem, you need to think slope of the tangent equals slope of the secant. So you are going to be finding slope somewhere, somehow, in some form or fashion. Okay, number 7. If f of x equals x plus sine of x, then what is f prime? Well, the first thing I would do, well, I've got to take the derivative. The derivative of x is 1, so I'm going to cross out all the answer choices that don't have a 1. And then what's the derivative of sine of x? Derivative of sine of x is cosine of x times the derivative of x. Again, we've got to take the derivative of that angle. Well, that's just 1. So my answer choice should be A. Hopefully everybody got that one. Right, and then number 7. This is part of a free response question. And let's see, for this one, part A, use the data from the table to approximate, to find an approximation for r prime at 45. So again, this is something we did way back at the very beginning of the school year. We're doing an approximation for r prime of 45 is approximately. So this is just like, again, kind of like the mean value theorem. We're going to use a rock to represent I rock. So 45, that's going to be between 40 and 50. And now I just use my slope formula. 55 minus 40, so I have 55 minus 40, that's the changing y's over changing x's, so to speak, over 50 minus 40. So that looks like that's going to be 15 over 10. Leave it, you don't have to reduce it. And we do need to talk about our units, so let's go up and read what our units are. The y's was gallons per minute, so I'm going to have gallons per minute per, and then notice the bottom was minutes as well. And please leave it just like that. All right, so part B, find the average rate of change of fuel consumption in gallons per minute during the airplane flight over the time interval from 30 to 70. So very similar problem here. We're going to talk about R at 70 minus R at 30 over 70 minus 30, or 40. And so that's going to give us R at 70 is 65 minus R at 30 is 30 over 40. And I'm tempted just to leave it like this. Or you can continue on, and that would be what, 35 over 40, and that's gallons per minute. Okay, another great review under our belts. Make sure you watch and understand all these problems, and if you have any questions, please feel free to ask me. I will be happy to help.